Hello everyone, my name is Willie. I'm going to introduce our work, Learning Code Query Interaction for Enhancing Code Searches. As we know, programming is sometimes hard because developers have little experience on the text or are unfamiliar with the programming libraries. In recent years, several DL-based code search methods have been proposed. They don't embed code snippets and neutral language queries into a high-dimensional vector space. However, DL-based code search methods still suffer from three problems. First problem, the OOV problem. Embedding techniques work well in NLP, but they encounter significant challenges in representing source code. As source code is inherently extensible, developers continuously define new functions and classes, or they combine or misleadingly use words. Second problem, the independently similarity matching problem. Existing DL-based methods embed the code and the query independently. They assume that in a high-dimensional space, if a code snap and a query have similar semantics, they usually occupy nearby regions. But a query is usually short and incoherent. Code snaps are usually long and have clear and coherent meanings. Therefore, embedding short queries and long code snaps into vectors of the same dimension is not conducive for understanding the query and lose the rich information in the code. The third problem is the small training dataset problem. DL-based methods usually rely on large-scale training datasets, while it is time-consuming and laborious to obtain such datasets. In order to build a dataset for code searches, an engineer needs to collect and filter projects. Even if a large dataset can be obtained, it is challenging to extract key features of code snaps. To tackle the above problems, we propose COIL. COIL uses a hybrid representation of source code and queries, and by applying the CNN, COIL achieves lexical and semantic similarities from code query interaction. The hybrid representation has a local representation part and a distributed one. In the local representation part, each term is uniquely represented. In the distributed representation part, each term is mapped to a compact, dense, and low-dimensional vector. COIL learns to match code and queries use a hybrid representation of code query interactions. First, COIL generates lexical and semantic matching matrix. Second, COIL leverages a CNN to capture rich matching patterns from matching matrix. Third, a MLP calculates the matching scores from matching patterns. The first component. To generate lexical matching matrix, COIL uses the local representation. To generate semantic matching matrix, COIL uses the distributed representation, and then COIL concatenates them. The figure shows examples of body query interaction matrix. In the left figure, each value represents the IDF value. In the right figure, each value represents the inner product of the term vector. The darker the color, the more similar they are. The second component. COIL extracts matching patterns through multiple layers of convolution and max pooling. The third component. COIL combines the final similarity matching patterns between code and snippets and queries, and uses an MLP to produce the matching score. To evaluate our method, we use two public datasets, CodeN and CodeBench. CodeN has over 18 million functions and CodeBench has about 500,000 functions. We compare COIL with 4 baselines. We use 3 metrics to measure the performance. The first research question is, how effective is COIL in code searches? From the table, we can find that among the IR-based methods, Lucene performs better than CodeHall. DeepCS can retrieve more relevant results than UNIF among DL-based methods. On CodeNN, the DL-based methods outperform the IR-based methods. Compared with DeepCS, COIL improved the MAP top 1 value from 0.58 to 0.69. On CoSbench, which is smaller than CodeNN, the IR-based methods are of similar performance to DeepCS, while better than UNIF. COIL outperforms the IR-based and DL-based methods and can increase their success rate top 10 value by 17%. Therefore, we have the first finding on both two datasets. COIL can perform better than the IR-based and DL-based methods. In particular, it outperforms DeepCS and UNIF by 13% and 18% in MLR on CoSbench. The second research question is the hybrid representation of code query interaction useful for matching lexical and semantic similarities? From the table, we can find that, compared with Lucene, COIL lock improves the result of MAP top 5 value by 15% on CodeNN. It also performed better than Lucene on CoSbench. COIL outperforms DeepCS by 5.8% and 12% on success rate top 5 on the two datasets. COIL with the hybrid representation performs better than that used local or distributed representation. Therefore, we have the second finding. Use the local and distributed representation of code query interactions. COIL capture lexical and semantic similarities between source code and queries. The third research question is COIL useful for a small dataset? From the line chart, we can find that with the different size of training datasets, COIL outperforms DeepCS and UNIF. Let it be trained on 115,000 samples. COIL outperforms the IR-based methods by 4.7%. So we have the third finding. COIL can use only 115,000 samples for training and achieve better performance than the IR-based methods. In conclusion, COIL uses both local and distributed representation of source code and queries, and apply the CNN to capture lexical and semantic similarities from code query interaction. Thank you.